So we're going to take the old equation we have for force of gravity, Fg equals mg. This is the one we're used to. There was always the caveat that it's only the equation that we use at the surface of the Earth. But let's imagine we're at the surface of the Earth. So now we have this equation, and now we have the new equation, Fg equals big G, m1, m2 over the distance squared. So just to be clear about this, what do we mean by m1? What do we mean by m2? And what do we mean by the distance squared? So what we're talking about is a situation where you're on the planet. So you're on the surface of the Earth. Maybe right here. This is exaggerated, obviously. So you're experiencing a force of gravity that's pulling you towards the center of the Earth. Now, the distance is always the distance to the center of the planet. So the distance between the center of masses of the two objects. So let's just draw it with a blue arrow. And it's like the distance from here to here is going to be d. Okay, that's the distance between the centers of the two objects. M1 and M2 are the two masses involved. In this case, we can call M1 the mass of the Earth. And then M2, we can call the mass of you, or of the person. The mass, let's call it the mass of the object. Okay, and when we have this equation, this is just the mass of the object. So in a sense, this one is actually M2, if we wanted to call it the same thing. All right, so if these are both equations that are equal to the force of gravity, then they should be equal to each other. So I'm going to set them equal to each other and just say mg is equal to g, let's just say this, mass of the Earth times mass, we'll just call the mass the object, divided by, and if you look at the way we've drawn this, d is actually just the radius of the Earth squared, right? Because distance is the distance from the center to the surface. That's just the radius of Earth. So when I do it like that, I can cross these two m's out because they're the same, both the mass of the object. And I'm left with this expression, G equals big G times the mass of the Earth divided by the radius of the Earth squared. So now let's just make sure this works. I'll give you some numbers. For example, we know that G equals 6.67 times 10 to the negative 11. The mass of the Earth is equal to 5.98 times 10 to the 24 kilograms. And the radius of the Earth is equal to 6.38 times 10 to the 6th meters. When you see these numbers, there's always like a bit of a plus or minus. So that's the numbers I recall. We can check on those later, but let's just use those for now and see how we do. All right, so let's plug those numbers in. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 6.38 times 10 to the 6th. And this is squared. I'm going to pause here and show you this on the calculator because I'll be honest, a lot of people make mistakes plugging this number into their calculator. So I'll pause here and then when we come back, we'll do it. We'll finish the problem. Okay, so bear with me here. I'm just going to type some numbers into the calculator. You might think this is obvious, but I just want to make sure everybody's on the same page. So we're going to plug in that equation, which is G, 6.67. Now, one thing I want you to use is second function and then comma. That gives you the exponent, and then we can put in negative 11. So that's how you type in big G, 6.67 times 10 to the negative 11, times, and then we're going to plug in the mass of the Earth, which is 5.98. Again, second function, E, 24, divided by, now I'm going to put parentheses around this. And I have the radius of the Earth, 6.38, second, E6, parentheses, and then I'm going to square that, and then I'll hit enter. And you can see what we get, 9.799, which is effectively 9.8, which is exactly what we wanted because we were trying to calculate G at the surface of the Earth. Okay, so we got our answer, and it is 9.799. The units, if you go through the whole thing, will work out to newtons per kilogram. Okay, and then that just rounds to 9.8. So we've shown that this equation can effectively get us the acceleration due to gravity, or the gravitational field strength on Earth. So just to be clear, this equation, we used it for the Earth, but we could use it for any planet, right? If we wanted to know G for Mars, we would just use G, mass of Mars, divided by the radius of Mars squared. Same thing, Venus, whatever, the moon, whatever planet you want, you can determine what the effective gravitational field strength would be on that planet by using this equation.